Welcome to another MECH 1000 video. In this video we're going to look at Unit 11 in the Blueprint Reading textbook, which is all about metric drawings. This is a pretty short chapter. I think we may get through this all in one video, so let's start. Metric drawings are becoming increasingly more common as business and engineering becomes more international. The United States is really the only major industrialized nation that still uses the English units of measurement. So the majority of the world uses the metric system. So if you do any type of business with a company outside the US, you're going to be dealing with metric units. So there are some benefits to using the metric system. For instance, in mechanical drawings, the standard unit of measurement is the millimeter, which is a pretty small unit of measure. The benefit to using a unit that small is that you rarely need to use fractions of a unit. So where we use quarters and eighths and 30-seconds and 64ths and their decimal equivalents, with metric drawings you may occasionally see a 1.5 or a 1.25 or something like that, but for the most part you're just going to see whole numbers, which makes it a lot more convenient. If you do ever need to convert between millimeters and inches, you can take those millimeters and multiply them by 0.03937 to get the inch equivalent. Metric drawings have already influenced drawings in the US. You may not have realized it, but we have adopted some practices used overseas. For instance, if you have wondered at any point throughout the semester why the symbols like radius or dimension appear in front of the number rather than after it, for instance, if we had a 0.5 diameter hole, the note says diameter 0.5 instead of 0.5 diameter. Well, that's the influence of metric drawings. So we are kind of becoming more universal in the way we represent things in mechanical drawings. Going along with that idea is the use of symbols. So symbols are preferable to abbreviations because symbols are not strictly tied to a language. This symbol here can be universally understood to mean diameter rather than the abbreviation DIA, which only makes sense if you speak English and understand the word diameter. So a lot of these symbols we have already seen. We have seen the diameter symbol used many, many times, as well as the radius symbol just being an R. I suppose you could argue that that is tied to a specific language, but it's just a single letter. We have spherical diameter, and that just represents a diameter that's three-dimensional rather than just a two-dimensional diameter, as well as a spherical radius, again, a three-dimensional radius. We have seen before in previous drawings that when a dimension is given inside parentheses, that means that it is a reference dimension. The thing to remember about reference dimensions is they are provided for your convenience, but they are not the dimensions that are to be used for manufacturing purposes, and the tolerance accumulates with a reference dimension as though you had to calculate it yourself. So you cannot treat it as though it were a given dimension. We have seen that dimensions that are underlined indicate that they may not be drawn to scale. That's usually the result of some type of drawing revision. We've seen the X used to indicate the number of times a particular characteristic is used. For instance, we may have 6 holes that all have the same diameter, and you would dimension that with 6 times diameter 0.5, or whatever that diameter happens to be. We haven't seen this symbol yet. It indicates arc length. It's an arc that goes over the number, and that tells you the length if you were to travel along the edge, along the perimeter of an arc from start to end point. What is that length? That would be contrasted with the chord length, that is the straight line distance from point to point. So the chord is straight line from beginning to end, and the arc length goes around in the arc curve. We've seen before this square symbol. If you're looking at something from a side view, we don't know whether the profile of that, if we were to look at it from the other direction, is circular, like a cylinder, or is it square, unless we have some type of symbol indicating in the side view that it is square. We've used the depth symbol, counterbore, and countersink multiple times. We've seen the conical taper and slope, and this symbol is used to dimension or indicate the origin of a dimension, like in the case of using datum dimensions or baseline dimensions. Now, the biggest difference, I would say, between metric drawings and drawings dimensioned with English units is the threads. That's where you're going to see the most difference. There's a whole separate series of thread specification for metric threads. So if you go to a hardware store and you're buying some nuts or bolts, you'll see that they have two separate bins, two separate shelves in the store for your English threaded nuts and bolts and the metric. Metric is a little less common here in the US, but of course they are the fastener series throughout the rest of the world. So there are some similarities between metric threads and the unified national system, but there are some key differences that we need to be aware of. First of all metric threads start with the letter M. So it's going to be a dead giveaway as soon as you look at it that, yes, this is a metric thread. There's an M right in the front. Now, the interesting difference is that because millimeters are so small, in the unified national system, we're typically given the threads per inch. For instance, a very common size is quarter 20 UNC. So that's a quarter inch, and the 20 is the TPI, the number of threads per inch. So in a 1 inch length, how many little threads are there? There's 20 of them. Well, because in the metric system 1 millimeter is so small, we would not have multiple threads per millimeter. We will only have maybe one. So what we do instead in the metric system when you have this series of threads is we actually just give the pitch, the length or size of just one thread. So when you see a number designated in a metric system, metric thread, you're being given both the diameter as the first number, and the second number is the pitch, not the number of threads per millimeter. Another thing to know about the metric system is there are only two series, coarse and fine. There's no such thing as extra fine in the metric system. So you may see some letters and numbers at the end of a metric thread specification, like 6H or 6G. These are similar to 2A and 2B, where in the unified national system, these indicate 2 being the general default class of fit, and A and B indicates internal and external threads. 6G or 6H and 6G are similar in the metric system. Now, a difference here is that in the metric system, it's not the letter that indicates the class of fit, but whether it's capitalized or not. So a capital letter H indicates an internal thread, or there's also G. So it looks like there's also E, F, G, and H, but G and H are the most common, and the capitalization or lack of capitalization indicates external or internal. Internal threads are capitalized, external threads are lowercase. There are also 3, 4, 5, 6, 7, 8, and 9 when it comes to class of fit, but 6 is the default standard class of fit. So 6H is the most common internal thread size, and 6G is the most common external thread size in the metric system. Here we have an example metric thread table. So you can see all of the metric thread designations start with the letter M, followed by the major diameter of the threads. In the smaller series, we do see a few decimals, 1.6, 1.8, 2.2. But then beyond that, we either see half millimeters, like 2.5, or for the most part, whole numbers, 8, 10, 12, 14, and so on. The second number indicates the pitch. How big is one thread? And again, in the smaller size threads, we are going to see some fractional portions of a millimeter. But once we get up to the bigger sizes, we tend to see just either whole numbers or maybe half millimeter sizes for those pitches. We also have in this chart the drill size that's needed to drill the tap hole that then gets the threads cut into it. So these drill sizes are going to be a little bit smaller than the final major diameter. So if you want to end up with a 1.6 diameter hole, you have to start by drilling a 1.25 hole. And then we have what that equivalent is in inches, what the equivalent drill size would be, and then what the equivalent size in inches are. For some of our sizes, we in the English system have both numbers, letters, and fractions. So we're a little bit less organized than the metric system. Okay, let's look at a few example problems here. The units of measurement used in this are actually called out here in a general note. That's not always going to be the case. In fact, a note like this is not always going to be present either. Sometimes you just have to look at the dimensions to figure it out. So if you look at the dimensions and you notice you're not seeing a whole lot of decimals, you're seeing primarily whole numbers, and those numbers are a bit larger than what you're used to seeing, you're probably looking at a metric drawing. The way these holes are located uses what AutoCAD would call ordinate dimensions. It also references back to one single point, which in this case is the top left corner. So the locations of all these holes are measured down from the top, and all of the horizontal locations are measured over from the left side. And so this is an example of datum or baseline dimensioning. I like to include this question because I think it's pretty sneaky. And I like to point out the fact that although in what this question is asking is, are the holes located by angular or linear dimensions? And you may look at this and see, oh, there's an angular dimension, 45 degrees. It's angular. But that angular dimension has parentheses around it, which means it is only a reference dimension. It's not the quote-unquote real dimension. The real dimensions are given down here in this table, where all of the holes are located with x and y coordinates. These x and y coordinates are linear or coordinate dimensions. And because the angular dimension is not the real one, it's only a reference, the tolerances are determined, again, by these linear dimensions. So it is the linear tolerance that controls. Last question here, I'm going to try to get in before time expires, is how many full threads will the tapped hole contain? The tap hole pitch is 2, meaning that each thread is 2 millimeters. The depth of the tapped hole is 28.6 millimeters. So if we divide 28.6 by 2, we get 14 full threads in this hole. So I'm just about out of time, but that does conclude Unit 11 metric drawings.